The home meal catering company in this particular scenario is a classic single work center scheduling problem. Let's take a look. The owner-operator of an in-home meal catering company has 4 jobs to deliver today, shown in the order that they were received. Okay, that's an interesting little note. Anyway, here are the jobs named W through Z. Here's how long each will take in terms of hours, and then here's where they've been promised. What's the first question? Suppose that the owner uses FCFS, first come, first serve, to schedule the jobs. How long on average will be required before each job is finished? All right, FCFS, first come, first served. What sequence would that be? Oh, right, that's why they mentioned here at the beginning of the problem that just in giving you the data on jobs W through Z, they're shown in the order they were received, which means that if you worked through them in that order, that would be first come, first serve. Oh, all right, so to address this first question, how long on average will be required for each job to be finished? Now, wait a minute. It's talking about the sequence that's being displayed, but how do you actually answer that question? What is another way to say how long on average will be required before each job is finished? Each job is finished, that is average flow time. That is just another way of saying what would the average flow time be of that sequence. Oh, okay, so for this data table, we need to calculate the flow time. Now, actually, this particular table, especially here on the note sheet, this is the sequence. We could probably create, like, just sort of stick in a little column in there. Squeeze it in, kind of, flow time. And just work with the data right here, because W will be first if the jobs are completed first come, first serve. W is 4 hours worth of work. That means that W will be finished in 4 hours. That's its flow time. X has to wait for 4 hours because it's second, plus X is 3 hours worth of work. So the flow time for X is 7. Let's see, Y would be next, but Y had to wait for 7 hours. Y is 2 hours worth of work, so the flow time is 9. And then finally, Z had to wait for 9 hours. Z is 1 hour worth of work, so the flow time for job Z is 10. And before I go any further, I want to check my math. This is the flow time of the last job in the sequence. It's 10. Go over to the processing time, just add these numbers up. These numbers add up to 10 hours worth of work in preparing these 4 in-home catering jobs. They add up to 10 hours worth of work, and this is not a coincidence. The flow time of the last job in any sequence should be exactly that number, and it is. Good. It was just a check on my arithmetic. Oh, all right, now we were still trying to answer question A. Question A is asking what's the average flow time? The average flow time, you just want to average those numbers. It's considered a quick measure of efficiency. When we say 4 plus 7 plus 9 plus 10 divided by 4, I get an average flow time of 7.5 hours. And say, well, okay. Now, what's the next question? If the owner uses shortest processing time to schedule these jobs, which jobs will be late and what will be the average job tardiness? Shortest processing time. Okay, first off, we're going to have to generate a new sequence. So we've got some room to work in here in the note frame, because now the topic is, and I'm just reminding myself, shortest processing time. What would the sequence be? I have to look at the data. Shortest processing time would sort these jobs by their processing time, the shortest one first. Oh, and it looks like really what we would do is just read up the existing data table, because Z is the smallest and W is the largest. I better write that though. We do Z first, Y second, X third, and W fourth, if we were following the shortest processing time rule. Now, what was asked is who's going to be late and what's the average tardiness. In order to assess if a job's going to be late in a sequence, or to calculate the tardiness, you have to calculate the flow time first. Oh, all right. So I'll make a column here for flow time. Let's see, Z will be done first. Z is 1 hour worth of work. The flow time for Z is 1. The flow time of the first job in any sequence is simply its processing time. Y will be next. Y had to wait that 1 hour, the flow time of the job before. Y is 2 hours worth of work. So the flow time for job Y is 3 hours. It will be finished in 3 hours. X had to wait 3 hours, the flow time before, plus X is, let me look this up above, 3 hours worth of work. So the flow time for X would be 6. It would be done in 6 hours. And then W had to wait till last. So W had to wait 6 hours in this case. Plus W is 4 hours worth of work, which means the flow time for job W is 10. And again, nice check on my math. The flow time of the last job should be the same thing as the sum of the duration data. It's that same old 10. Good. Okay, now this still doesn't quite answer the question. The question was about who's late and what's the average tardiness. Now we need to add a column for that. Okay, that's when they'll be finished, right? But who's tardy? Who's going to be late? Well, let me see. Z will be finished in 1 hour. I scoot up here to look at the due date. Z was promised in 1 hour. Oh, so Z's not going to be late. It's going to be right on time. Yes, its tardiness is 0. Y will be finished in 3 hours. Y, a little bit of a problem, was promised in 2 hours. So the tardiness for job Y will be 3 hours when we get done, minus 2 hours when we said we'd get done. We will be running 1 hour behind. Let's see, X will be done in 6 hours. What was X promised? X was promised in 9 hours. No problem. X will be done early, which means the tardiness is 0. And then W. W will be done in 10 hours. W, let me find it. Oh, we do have a problem here. W was due in 5 hours, so the tardiness is 10 minus 5 hours. Oh, okay, now, what's the question asked? Which jobs will be late? We can do a little report here based on this. We can see that Y and W will be late. Y and W will be late. We can see that from their tardiness. Oh, and then what's the average tardiness? We need to average 0, 1, 0, and 5. So 0 plus 1 plus 0 plus 5, that's 6. 6 divided by 4, average tardiness equals 6 divided by 4. We're just averaging these numbers here, or 1.5 hours. All right, that is actually addressing the questions right here. Good. We're done with that section of the scenario. What else do they want to know? If the owner uses earliest due date, now we're talking about a different rule, earliest due date, which jobs will be late and what will be the average lateness. Oh, okay, so this is essentially the same exercise as the question before we were just working on, except we have to generate a different sequence because they're asking about a different rule. Oh, okay, which means that we still go through the same steps. First, generate the sequence. Now, earliest due date means you sort by the due dates, the earliest or the smallest first. So looking at the data, that looks like you'd do Z because it's the smallest, then Y, oh, then W, then X. I'm going to want to note that. Z would be first, it's due the earliest, then Y, then wait a minute, then W, and then X has to wait till last because it has the farthest out due date. And again, in order to assess tardiness and to see who's going to be late, we need to first calculate flow time. So the flow time of the first job is just its duration, that's 1 hour. Let's see, the flow time of the second job, Y, had to wait that 1 hour. Y is 2 hours worth of work. The flow time is 3. W had to wait for 3 hours. W is 4 hours worth of work, so the flow time of job W in this sequence is 7. And then X had to wait for 7 hours. plus X is 3 hours worth of work. Good. It still winds up being 10, the flow time of the last job. Now, that was so we could then assess tardiness by comparing these jobs to what we were told about when these are due. Let's see, Z is due in 1 hour. It's not going to be tardy. Y is due in 2 hours, so it is going to be tardy. It's going to be 1 hour tardy. W is due in 5 hours. If we get done with it in 7 hours, that means we're running 2 hours behind, a tardiness of 2. And then X is due in 9 hours. We're going to get done in 10, so here we're running a little bit behind as well, 1 hour. Okay, so, to answer the question, right, turns out earliest due date, Y, W, and X will all be late. However, average these numbers. Remember, they asked for the average tardiness. So average 0, 1, 2, and 1, that's 4. 4 divided by 4. 4 divided by 4 is 1. The average tardiness is lower. The average tardiness here is lower than it was with shortest processing time. Even though with shortest processing time that had an average tardiness of 1.5 hours, there was only 2 jobs that were late, but they were kind of like more late. Okay. Now, last question. Which sequence is most efficient? First come, first serve, shortest processing time, earliest due date. These were the 3 that we were looking at. Oh, okay, now we have 3 different sequences and the in-home caterer only wants one of them. Which one is the most efficient? Generally speaking, mechanically speaking, we say, well, whichever one has the lowest average flow time is the most efficient. In that's what average flow time is considered a good, quick, simple measure of, is the general speed or efficiency of the schedule. Although one would argue, especially with something very customer service oriented like catering, that we can't leave the deadlines out of this as well. So actually, might as well, it's good practice, is why don't we line up both these issues in a table? We're trying to pick from or comment on here first come, first serve versus shortest processing time versus earliest due date. All right, now there's 2 measures, 2 performance measures, average flow time and average tardiness. And what do we know? Actually, we can just fill in some data here because, for instance, we were just looking at earliest due date. The average tardiness is 1 hour. I can fill that in. And we were looking at shortest processing time. The average tardiness was 1.5 hours. We had already figured out the average flow time for first come, first serve. That was 7.5 hours. We didn't figure out these other ones exactly, but that's what I mean by good practice. You know, we might as well do that. Okay, so for instance, shortest processing time. What is the average flow time for shortest processing time? Well, you would want to gather up the flow times for the shortest processing time sequence, and I did that. That's the 1 plus 3 plus 6 plus 10. And you're averaging, you know, so you divide by 4. So the shortest processing time, the average flow time for the shortest processing time sequence is 5. You know, which is quite a contrast to 7.5 for first come, first serve. But anyway, okay, so we have a number for here. Then the same thing with earliest due date. We didn't bother to calculate the average flow time, although we calculated the flow times. They're above here on this page, 1 plus 3 plus 7 plus 10. Divide that by 4. You know, it's always going to end in 10. All right, I get 5.25. So we're still trying to comment on who's the most efficient. If you want to do this based strictly on flow time, then we definitely would say, well, you're just looking for the smallest number here. You say, well, shortest processing time. And that's not a coincidence. These are heuristics. There's no guarantee. But generally, shortest processing time minimizes average flow time. And you see here, it does deliver the lowest average flow time. Oh, but by the way, well, you know, there's just one for the sake of completeness. There's just one point on my little table that's not filled in. And that's for first come, first serve. What was the average tardiness for first come, first serve? It's good practice, right? Let's see, average tardiness for first come, first serve. We need to, here we go, squeeze in another column for quickly tardiness just by comparing this to the processing time. Oh, well, W would not be tardy. Let's see, excuse me, no, this to the due date, sorry. This to the due date, W would be finished early, right? X will be done in 7. X was promised in 9. It will be finished early. Let's see. First come, first serve. We'll finish Y in 9 hours, but it was promised in 2. That's not good. It's going to be 7 hours tardy. And then we'll finish Z in 10 hours, and it was promised in 1. That is definitely not good. That's a tardiness of 9, which is to say average tardiness. What's the average tardiness there? Well, it would be 16 divided by 4. Do you see how it is much, much larger than these other two? When it comes to flow time, which is a general measure of efficiency, shortest processing time generally minimizes average flow time. We say it's the most efficient. We do want to note here, though, that earliest due date delivered the best average tardiness, of which that's not a coincidence either. It generally does. Notice that first come, first serve isn't really strong on either dimension, right? It's got the larger numbers in either case. Because first come, first serve, as a priority sequencing rule, doesn't have a reputation for being particularly efficient or particularly good at minimizing tardiness. Well, then why do we have that rule? Because first come, first serve is the rule that, generally speaking, if it's people that you're sequencing, that everybody agrees is fair.